I hope you are good. You are running the code well, or let's start it. So in his code, in his project, the Bob Kopp want to reconstruct common era global mean sea level change during that 2,500 years. So to do that, remember that if we talk about kernels, if we want to reconstruct global mean sea level from the kernels, we do need a global data set of sea level change. So what he actually do is he kind of compile a proxy data across the world. It's not always across the world, but it's some part of the world. More data is available in North America and Europe because of the historical reason that more data is there. And he also incorporates some high gauge data that can tell him better with the sea level change in the last 200 years. So the first thing we do is we load the proxy data and we load some high gauge data. And there are some old high gauge data he get it or somebody get it from some book or some old recording. So we load that data as well to our data set. And because of the proxy data and high gauge data have different resolution, and you know that the GP model becomes really slow. We have too much data. So he makes the decision that he wants to smooth the high gauge data to decadal average value. So it's kind of first let the high gauge data have the same resolution as the proxy data and kind of reduce our computational burden. I will show you how to do that code straight away. And then you want to use, because there are multiple studies to reconstruct sea level change globally during the 20th century. So he used a Hay et al. 2016 paper in terms of global mean sea level reconstruction, using them as a data to form the model of how much global sea level change after 20th century. And there is something special called flattener. So he used a flattener to ensure the sea level at between -200 to 200 is the same as I think it's the same as the 1600 to 1800. So in this case, it kind of provides a baseline of sea level change because he assumed there is not much sea level change between these two time periods because there is not much anthropogenic forcing to this to the climate back then. And he used I5G model to remove the GIS signal. So basically he tried to use I5G model as a mean function in GP model as we did before. Okay. So how did you do that in PaleoSTEHM? Okay, so let's try to do that in PaleoSTEHM. Okay. So if you can go to here, 8, very left is we can use them to regenerate Bob Kopp's results. So here we are loading the proxy data and high gauge data. And then we are loading the global mean sea level reconstruction by Hay, 2016, I think. And here is we build a flattener to enforce the sea level between -100 to 100 C descent at the sea level at 1600 to 1800 C. Okay. So this can be useful because when you do not have enough data, you kind of embed your prior knowledge into this level model. But after that, it's kind of almost a year after this project, there are more and more sea level data become available. So now we are trying to get rid of this flattener. Okay, so now we are loading 3 really old high gauge data here in this cell. So I encourage you to read this code a bit later. Okay, but you just need to understand what it's doing in each code block. And then we are trying to smooth the high gauge data to take the decadal average, right? There are some code for you to do that. I have already done that for you, so we just load data. If you want to do that, you just uncomment this code. So the code will help you to do that. And we smooth the old high gauge data with the decadal average as well. And then we have a lot of data, right? We have proxy, we have high gauge, we have old high gauge, we have global mean sea level reconstruction by Hay 2016. We have flattener, so we kind of combine them together, and we try to filter out any kind of data that would have really large uncertainty in their temporal resolution. Okay, so this is what we do here. So I want to show you like what does the flattener, how does the flattener and global mean sea level look like as data. Okay, so here is, okay, we haven't installed necessarydependencies. Okay, so let's install necessarydependencies here. So here is like we try to import I5G data and remove I5G from our GIA, from our sea level data. So here is like we kind of remove the GIA signal using a GIA model and remove them from the original data. So we are modeling essentially the Y without GIA. Because we are moving the GIA signal, our lasting signal reflecting a little bit better with the global mean sea level we try to reach. Okay, so let's try to build this model. So the kernel is exactly the same. There's a global kernel, there's a regional linear kernel, there's a regional nonlinear kernel, and there's a white noise kernel, and there's a spatial white noise kernel. So a spatial white noise kernel is that the kernel you use to add a noise to different sites. So for each site, you add some noise and add some correlation to capture the site-specific. Okay, and lastly, you just combine all of this kernel together, and everything we use for flattener is like we modify the covariance, data covariance matrix. So the way we add a flattener is that we add some synthetic data that covers specific area where you have really large uncertainty in terms of their Y value, but they are highly correlated, right? So the data, so the synthetic data between 100 minus 100 to 100 dB is highly correlated to the synthetic data between 6,000 to 8,000. So because they are highly correlated, they will force the global mean sea level to be the same at these different time slices. Let's check out how that looks like. And I think the RAM is going to have some problem in my lab. So let me just show you. Okay, so that's this is the flattener covariance function. Okay, I'm going to show you. Okay, you see that in the diagonal, so the variance for each kind of synthetic data is really low. So actually, if you see that this 4 data points is kind of from -100 to 100 DE, and they have really high correlation between the data points at 600 to 1800 DE. So that's why they have a higher correlation. So that's why you see the resulting construction that here is sea level between -100 and 100 to 600 and 800. I think it's 600 to 1800, kind of similar. Okay. So, and then I want to show you what is Hayes global mean sea level reconstruction embedded this data in this model. So let's try to find what here. Okay, so this is Hayes model's covariance function. So you can see that maybe that's the overall noise covariance function. You have a better idea. So okay, so you can see that this is the covariance function, like Hayes embedded in our data covariance function. So the data covariance function is basically meaning, I talked about that yesterday, is let me show you. Might be a bit overwhelmed, but let me just show you data covariance. Oh, it's not. I talked about it yesterday. The paper. So the data covariance function basically means you have a variance value for each data, which you might quantify from geological reconstruction, and each kind of column here is the covariance between 2 data points. So if you think the data point is independent, the covariance between them is 0. But if you think there's a high covariance between your some data points, the covariance is high relative to the variance value. Okay, so here we include the Hay et al. Global mean sea level reconstruction, and you can see that the variance of Hay et al. 2016 is very low comparing to other signals. Okay, let me show you. You see here the variance is, I think variance should be pretty low. Let's just put the variance. You can see that the variance here is pretty low compared to previous data. So in that case, our reconstruction really pay attention to technical global mean sea level reconstruction. So let's try to do some prediction with this 2P model. So this is kind of so now you can see the prediction here. You can now start to predict decompose the global mean sea level change using this data across the world and using this engineering I talked about before. So some of them might be less intuitive now, but if you go to see the code yourself, it will become more clear. Okay, and then I just compare our reconstruction with COP et al. 2016. The reason why they are slightly different is that we are using different optimization algorithms, right? But if I'm using the same type parameter by COP et al. 2016, we can well replicate the results by COP et al. 2016. So then we can make some interesting interpretation of global mean sea level change during the past. And here you can see that I can quantify the global mean sea level change between 0 to 700 CE is like 0.09 millimeter per year, and 1,000 to 1,400 CE is around negative. Global mean sea level is dropping for some, but the uncertainty is quite large. And then you can try to do some interesting thing based on the global mean sea level reconstruction. You can try to